Hello, my name is Gary Weiss, and today I'll be presenting our research paper, Predicting Student Performance in the Master of Data Science program using admissions data. This is research that was done collaboratively with Yijun Zhao, Changpeng Chu, and Ming Chen, and we're all from Fordham University. So the general motivation is to address an important problem, which is admitting good students. So more specifically, the goals could be enroll the best students, enroll the students most likely to graduate in a timely manner, perhaps enroll students who will require the least amount of financial aid, enroll a diverse student body, or enroll students that are most likely to accept the program and enroll. However, our main goal in this case is to enroll the students who will perform well academically in the program and avoid the students who will not perform well academically. So our goal is to admit students into our MS in Data Science program that will perform well academically. More specifically, we want to be able to identify the very top students who we probably want to give merit-based financial aid to, and also the bottom students because we probably don't want to admit them. In addition, we want to better understand the factors that are most relevant to student performance in our program. This is useful for a lot of reasons. We can certainly update our admissions policy, but it's also good for us to have an understanding of what is and what is not important. This is kind of interesting problem because we're focusing on graduate admissions, and certainly undergraduate admissions gets the most attention and has been the most studied. Also, we're faculty who don't have highly specialized training for admissions, as opposed to undergraduate admissions where you have professionals where that's basically all they do. It's admissions and basically promoting the program. Also, our program is interesting because it's interdisciplinary. So that means we have very diverse students with very different undergraduate backgrounds, and that makes the admissions task a little bit more challenging and interesting. And we're not even clear exactly what are the most important backgrounds and skills that the student should have. We generally think they should have strong computing and mathematical skills, but we're not quite sure what the relative value of both of those are, and not all students will have very advanced skills in both of those. So we basically have to try and figure out what are the most important skills. Now, if we talk about the data, um, we have 826 applications data for the program. Of those, 61% of the students were accepted and 39% were rejected. Um, of those that were accepted, only 132 actually enrolled. So our data set is actually made up only of enrolled students because those are the only students where we know their actual grades and how they performed in our program. So it's a relatively small sample size. We use structured data, we don't use unstructured data. So in the application material, we have a resume, recommendations, and personal statements, and these are all textual, and maybe in the future we could use those, but we don't currently use them now. It would not be very straightforward. But there is a lot of structured data, and we show the key features on the right. There's standardized test scores like the graduate record examination scores. There's some demographic information related to the student, and there's 6 fields or features that relate to the prior school that the student graduated from. And that is typically their undergraduate institution, although in some cases they may have also completed a graduate program, in which case we would use whatever the most recent graduated program is. And then finally, what we have at the very end is their performance in our program, which is their GPA in the Masters in Data Science. Ultimately, we're not going to try and predict that, but rather use that value to form bins and classify them based on which bin they're placed in. Although our focus is going to be on analyzing the enrolled students, it is useful to understand a little bit about the students who were rejected and not admitted into the program. So if we look at this, we can see that students who have under a 3.0 GPA make up 41% of rejected applicants, but only 15% of those who were admitted. If we looked at the reputation of the school, we see that 31% of the rejected applicants have a school that's ranked, that's a school they graduated from, that's not in the top 2,000 globally. and it's much less for the admitted students. If we look at the actual majors, and we can look at the chart on the right, we can see that most majors who apply are from CS or EECS, or math or statistics. If we look a little bit more detail at the ratio of the admitted versus not admitted, we see that a higher percentage of the CS students are admitted than even for the math and stats, and it's significantly higher than for the economics and finance students. So next we're going to look at the features and how the feature values relate to the different performance categories. So we're going to look at students who graduate with GPAs in the bottom 20%, top 20%, and middle 60%. So one of the things that we notice from this is that the students in the top and bottom 20 percentiles do not have huge differences in their GRE quantitative scores. And that's kind of interesting because that's one of the key factors that we focus on. Probably the reason that they're not very different is all of the admitted students generally have pretty good math GRE scores. So we can also look at some other factors. It's notable that foreign nationals tend to be much better represented in the top category. We're not exactly clear about why. It's possible that perhaps they have better backgrounds and more appropriate majors for this degree. Also, students who have completed a graduate degree tend to be better represented in the top 20 percentile. TOEFL scores don't seem to have a big impact. Maybe that's not surprising because if a student has a very low TOEFL score, then we cannot admit them. But probably the factor that is most interesting and has the biggest impact is the school GPA from their prior school. If we look at the values here, we see that those in the bottom 20% for their MSDS GPA, for the undergraduate GPA, or their last GPA for their last school is 3.17, in the middle 60% is 3.29, and the top 20% is 3.53. So we see that there's a clear relationship between their last GPA, which is usually for their undergraduate college, and how they perform in our program. So next I want to talk about our experiment methodology. We formulate the problem as follows. We want to distinguish the students who are in the bottom 20% and the top 20%. And we formulate this as two binary classification problems. So the top 20 versus the rest, and the bottom 20 versus the rest, because this simplifies the modeling process. We use a large number of classification algorithms. They're all quite popular. And we'll show the results for each of these and see which ones perform the best. As far as the actual design of the experiments, we use tenfold cross-validation to maximize the use of our data. And there is substantial class imbalance because in each case, we have one sample, which is the class we're most interested in, which is 20% of the students, and the rest is 80%. So to deal with the class imbalance, we create 5 samples, where in each sample we include all of the students in the 20% and then 20% of the students randomly chosen from the remaining 80%. So this way we use all of the students, but each sample has a balanced distribution, and this tends to give us pretty good results. Okay, so now we're going to look at actually the results of the experiments. So if you look at this table, you see we have all the different classifiers lined up. And then we have the two binary classification problems where we try and distinguish between the bottom 20% and the rest, and then the top 20% and the rest. And we measure the performance of the people in the 20%, either bottom or top, and that's in terms of their true positive rate. So if you look at these, we can focus mainly on the classification algorithms that perform best. So if we look at the overall average or accuracy, we'll see that the ensemble classifier and the random forest classifier generally do best. So let's just focus on those. Now, if we look at how well we do on the bottom 20% or the top 20%, we generally have an accuracy over 90%. So that means we can pretty effectively identify the students who are either in the bottom 20% or the top 20%. And this is actually pretty impressive when you think about the fact that these are only the students that were admitted and enrolled. So the students who, let's say, had a very bad backgrounds, maybe low GRE scores and low GPAs, they've already been winnowed out. So all of the students in this population have fairly reasonable credentials. So I think that makes the results even more interesting and impressive. So this basically shows that we can do a pretty good job at predicting how these students will perform in the program. So now we can look at which features are most important in the models that we build. So we're going to look at the top 10 predictive features for some of the best performing algorithms. And all of these algorithms have a way of identifying which features are most important in building the model. So if we look at these, first of all, I would point you to the footnotes at the bottom that help explain what some of these features represent. So for example, if we look at the bottom 20% and the most important feature for SVM, we see that it's whether your major is economics or not. So if you're an economics major, that is most useful in distinguishing whether you're in the bottom 20% or the rest of the population. Similarly, for the top 20%, it's whether you're a business major or not. And we're not saying that business majors are in the top 20%. We're just saying that that's useful in distinguishing whether you're in the top 20% or not. And in fact, business majors tend to do poorly, and they're less likely to be in the top 20%. So if we try and look at some of the takeaways here, we see that for models like SVM and logistic regression, features like the prior major, level of education, and country of origin are most important. If we look at decision trees and random forests, we see some of the quantitative metrics are most important, like GRE scores, prior GPA, and school ranking. And previously we mentioned that prior GPA is very important. So again, that's just confirmed here. As far as the GRE scores, if you recall, I said that the quantitative GRE scores really didn't differ much between the bins. So here it's actually the verbal GPA that is actually what is useful for distinguishing between these two. And that is something that is a little bit surprising to us and something that we don't normally focus on too much in the actual admissions process. So I suspect it's not necessarily that verbal abilities are more important than quantitative abilities. It's just that most of the students who apply to the program have high GRE quantitative scores. So the small differences that exist really don't matter that much. But they have very different, potentially very different scores when it comes to their verbal abilities. If we look at support vector machines and logistic regression, not only can we identify which are the most important features, but we can actually identify their magnitude and how important they are. And one of the takeaways, if we look at the details here, is that for business, economics, and communication majors tend to do quite poorly, whereas computer science and math majors tend to do quite well. So that's something that we kind of take into account in the admissions process, but this really confirms what we already suspected. Okay, so our research showed that data mining can aid with this very challenging task of admitting students into an MS program in data science and help us identify the students who will perform best and the students who are likely to perform worse. In general, at identifying these two populations, the best and the worst, we can have accuracies of around 90% by using our models. A variety of factors affect the outcome, and the models did suggest which factors were most important. They did differ a bit based on the classification algorithms, but overall I think we can say that the prior school GPA and the undergraduate major were the most important factors in whether a student will succeed or not. So there's some limitations to this work. One limitation, which we already mentioned, is that our data set only involves enrolled students. Clearly we don't have GPA information about students who were rejected. It's probably not a good strategy to admit all students just so that we can see how students who are not well prepared or have low GPAs would do in our program. Also, our data set is relatively small. We only have 132 enrolled students, so that is a significant limitation that might impact the generalizability of our results. So in the future, we can address some of these. We plan to rerun the analysis in a few years when we have a lot more students. We'd also like to extend our analysis to our other master's programs in cybersecurity and computer science. And we'd also like to use semi-supervised learning to utilize the unlabeled data that we have from students who were rejected or accepted and don't enroll in the program, and perhaps use something like SVM Plus so we can exploit that unlabeled data, which could potentially give us improved results. So that's it for the talk, and I'd like to thank you for giving me your attention, and I'm sure my co-authors also appreciate you watching this video. Thank you.